Have you ever been watching your phone and the internet speed just feels like it has a mind of its own? You know, blazing fast 1 second and then just kind of meh the next. Well, what if I told you that's not a bug? That inconsistency is actually one of the most brilliant features of how our wireless networks work. Okay, let's get into it.
So yeah, why the roller coaster ride? Why is it that you can stream a perfect 4K movie in one spot, but then walk a few blocks away and struggle to even load a web page? Well, the answer isn't that your network is broken. It's actually the opposite. It's constantly and really intelligently adapting to the laws of physics to give you the absolute best connection it can, wherever you are.
And it all kicks off with the most basic challenge in all of wireless, just getting a good, strong signal. This is the foundation everything else is built on.
I mean, this part is pretty intuitive, right? The closer you are to a cell tower, the stronger and cleaner that signal is. But the farther you move away, the weaker and fainter it gets. This one thing, how far you are from the tower, is probably the biggest factor in what your potential speed can be. A strong signal opens up the possibility for super high speeds, but a weak one, that forces the network to play it safe. But how does a network actually know how fast it's safe to go? It's not just a guess. It's all governed by this beautiful fundamental law of physics, figured out by the genius engineer Claude Shannon way back in the 1940s. He basically gave us the ultimate universal speed limit for any communication channel. Now, to get Shannon's limit, you first have to understand one really important idea, the signal-to-noise ratio, or SNR for short. The best way to think about it is like trying to talk to a friend at a loud party. The signal is your friend's voice. The noise is all the music and other people talking. If you have a high SNR, your friend's voice is crystal clear. But with a low SNR, you're leaning in, yelling, "What?" all night. It's the exact same for your phone's signal. And that brings us to this, the Shannon capacity curve. What Shannon proved, mathematically, is that for any given level of signal clarity, any SNR, there is an absolute, unbreakable speed limit. You just can't push data faster than this line without it turning into garbage. The better your signal, the higher up the curve you can go, and the higher your speed limit is. This curve is basically perfection. It's the theoretical max. And the difference this makes is just dramatic. Look at this. With a really great signal, let's say a high SNR of 12 decibels, your theoretical speed limit might be 400 megabits per second. Awesome. But if your signal quality drops and your SNR is only 5 decibels, that speed limit gets slashed in half, all the way down to 200. Your phone is constantly measuring this, so it always knows exactly what that speed limit is, second by second. So here's the big puzzle for the engineers. How do you build a system that can gracefully adjust its speed to ride that Shannon curve as closely as possible without ever falling off? Well, it turns out they use a really clever two-tool solution. The first tool is called adaptive modulation. I want you to think of this like the gearbox in your car. When conditions are perfect, clear open road, you can shift into a high gear and go really fast. The second tool is called forward error correction coding. This is your safety net. It adds a little bit of protective, redundant information to your data just to make sure it arrives safely, even if the road gets a little bumpy.
Okay, let's look at that gearbox first. When your signal is weak, the network uses a really simple gear, like QPSK. It only packs 2 bits of data into each signal. It's slow, sure, but it's super reliable. But as your signal gets better, the network starts shifting up to 16 QAM, which packs 4 bits, then 64 QAM with 6 bits, all the way to 256 QAM, which crams an incredible 8 bits into that very same signal. That's how it floors the accelerator when conditions are right.
And now for the safety net, the coding. The network takes your data and adds some extra parity bits. These don't have any new info, but they act like a little checksum, allowing your phone to find and fix errors caused by noise. The code rate just tells us how big that safety net is. So a code rate of 3/4 means that for every 3 bits of your actual data, the network adds 1 protective bit, sending 4 bits in total.
All right, so we've got a gearbox for speed and a safety net for reliability. But here's the real magic. Here's the aha moment. It's how these two tools are combined to not just get close to Shannon's perfect curve, but to hit almost any exact point right on it.
It all comes down to this really simple but incredibly powerful bit of math. You take the speed of your gearbox, the modulation rate, and you multiply it by the strength of your safety net, the code rate, and that gives you your exact effective data rate.
And this example just illustrates it perfectly. Let's say Shannon's curve says the absolute maximum safe speed right now is 1.5 bits. The problem is, our gearbox doesn't have a 1.5-bit gear, right? It's got a 1-bit gear and a 2-bit gear.
So what does the network do? This is so clever. It shifts into the higher 2-bit gear, but then it applies that 3/4 safety net. So it sends 2 bits, but only 3/4 of them are your actual data. And what's 2 times 3/4? Boom, exactly 1.5. It hits the target perfectly. By mixing and matching these two tools, it can create hundreds of these super precise speed settings.
So this isn't just some cool theory in a textbook. This is literally what's happening inside your 5G phone thousands of times every single second. Let's look at how the whole system actually works.
The whole system runs on something called a modulation encoding scheme table, or an MCS table. The best way to think of this is like the team's playbook. It's a huge list of every possible combination of a gearbox setting and a safety net setting, and each one has its own special number. Your phone has this playbook, and the cell tower has the exact same one.
And this is how that invisible dance happens. Step 1, your phone is constantly measuring your signal quality, that SNR. Step 2, it looks at its playbook and finds the perfect combination for the current conditions, and just tells the tower the number, like use play number 17. Step 3, the tower gets that message and immediately starts sending you data using that exact play. This whole loop happens over and over, super fast, making sure you're always on the most efficient setting possible.
So with all this technology, how close do we actually get to that perfect theoretical Shannon limit? Well, it's incredible. The coding used in modern 5G is so efficient, it can operate with just a 1 decibel penalty from the absolute physical maximum. To put that in perspective, older tech was like 7 or 8 decibels away. That is a massive, massive leap in engineering.
So the next time you see your internet speed change, don't think something's wrong. Instead, picture this. A constant, invisible, high-speed dance happening between your phone and the cell tower, both working together to give you the fastest, most reliable connection that the laws of physics will allow right in that very moment. All right, so let's just quickly recap the big ideas here. Your speed is always changing because your network is smart and it's adapting to your signal quality. There's an ultimate speed limit for everything, set by Shannon's law. And 5G uses that amazing combination of a gearbox and a safety net, all managed through a shared playbook and a crazy fast feedback loop to get as close to that limit as humanly possible. This whole invisible system is what keeps our connected world running. But it really makes you wonder, doesn't it? As our appetite for data just keeps growing and growing, what other amazing, hidden technologies are engineers dreaming up right now to keep us all connected in the future?